Okay, so in our last class when we did the introduction, Zach mentioned that we have that cybersecurity club. If anybody's interested in that, by the way, there are circulars here you can pick up after class, and that'll tell you what you need to do if you're interested in joining that. So that's my housekeeping item before we start. So, what we're going to do today is we're going to start to learn the language that you're going to hear in this class. And it's important that you know what they mean. So, we're gonna talk about relations, and we're gonna talk about and schemas and all that good stuff. And some of those words may be familiar to you, and some of them may not. So today is all about the language of databases and relational databases in particular. So let's get into that. We already started this a little bit because we about differences between a database and a repository. A repository like the internet is just a collection of files, so a search engine isn't really a database management system. So if you think about collections of data, they can be structured or unstructured. If they're unstructured, I tend to think of them more as a repository of data rather than a database. If they're structured, they're more of a database. And we talked about some of the databases that we encounter in our daily lives in different industries. Here's a list of those. Some of these we mentioned, but most companies have information about sales. They keep their sales data in a database that includes customers and products, what those customers buy. So, you can think of Amazon as a big database. They have all your information about you as a customer. They have all that information about products. And they have all the accounting information, your credit card information, which most of them don't protect very well. And you wind up getting notices saying that you've been part of a compromise, and you get free identity management services for a year and things like that. But, they keep that stuff, and they're supposed to protect it. Most enterprises, including this college, have information about personnel. So personnel databases. So, that includes things about employees. Factories. One of my favorite things that I did when I was in my career was I got to visit a factory that we used to manufacture telecommunications equipment. And everything was automated and everything was data driven in the factory. And it was really amazing how that worked. They keep inventory, they keep orders, they keep information about their various suppliers and things like that. So manufacturing is a very automated area. Let me ask you guys this. Do you know of any companies that exist simply to provide some of these databases? Have you ever heard of any of these companies that do these things? Like HR databases or manufacturing databases or things like that? There are some out there. I guess there's ADT does HR stuff. There's a company called PeopleSoft you might have heard of. There's a company called SAP. They do sales databases. So like if you go into an industry and you want a generic sales database that includes all of this stuff, a lot of companies go to SAP and they implement SAP's database in their environment so that they don't have to build it themselves. There are a lot of good, yeah. Yeah, no password. Just hit enter and you should be in. So if you're fortunate enough to work for one of those companies, you're going to be doing a lot of database work if that's what you're interested in doing. Those are good companies to work for. Oracle has a number of their own solutions that they provide. Oracle HR, Oracle manufacturing. So there are a number of companies that are just in the business of providing database solutions. And then there are a number of companies who use those database solutions. And that's another way that you might encounter this as you enter your chosen profession, most of you being computer science majors. Banking and finance, another key area where they use databases extensively. All of your automated banking is based on a database. all of the credit card companies, or all of the companies that accept credit cards, all the payment card industry companies, all use databases. And of course, we talked a little bit about our own college here and the databases we use, including, if you go on Ocean Connect, you will see about probably about 10 to 15 different databases that Ocean County College uses. If you look at this list here, you'll see, for example, you've got Handshake, that's a career database. Some of you guys might have been using. You'll see Student Clearinghouse, that's just a big database. Advising, all that stuff. Student planning, the thing that you use to register for your classes, all of that stuff. All of these things are individual databases that Ocean County College uses. And the one that we use to drive this course is Canvas. That's one of the databases in the college. So, the bottom line here is, that learning database is good because you're going to run into it in whatever your chosen profession is. And just a couple more here on the next page. We have airlines and travel. We have telecommunications. A big deal for a while was that telecommunications companies were keeping track of your communications and providing them to the government. So, they maintained a large database of all your calls and things like that. And that was supposed to be private, but, what's his name? Edward Snowden revealed the fact that, all that information was being provided by the communications companies. So, that's, if you're in telecommunications or if you're in government, you'll likewise use databases. All right, so those are just some examples, and you guys hit on a lot of them the other day. But, database systems exist to maintain the accuracy, confidentiality, accessibility, all those things about the data. So they need to do a lot of different things to store and deliver and protect and maintain data. And those things are done by a database system. And database systems generally abstract the details of how that's implemented from you. So when you issue a query or a question against the database system, you don't know how they're retrieving the data. They can store and retrieve that data in a number of ways. And for those of you who are taking data, is anybody taking data structures, or is anybody taking the data structures class? Okay. In data structures, you'll learn a lot more about how databases are implemented. Things like hashes to make data retrieval faster, things like indexing of data, or various methods of data retrieval. So this is my commercial message. If you're interested in using a database system, you come to this class, a database management system. If you're interested in building one, you might want to take a data structures class also. And so here you're going to learn to build databases and access databases. In data structures, you'll learn how to implement database management systems. Okay. So, another thing that database management systems do, or database systems do, is they make sure, for example, that certain operations occur either completely or don't occur at all. So, for example, if you're doing a funds transfer, you're transferring funds from one account to another, you don't want that money to disappear from the one account without appearing in the other account. So things like that have to happen together. So database systems make sure that, things that have to happen or depend on one another are executed atomically. So you'll see that term in database systems also. You'll see it on on this slide, atomicity of updates. Things happen as a unit. Does anybody know what it's called when you do some set of operations on a database together as a unit? It's called a transaction. So we're going to learn a little bit about database transactions in this class. Transactions combine multiple operations against the database and are only successful if all of the operations are successful and is unsuccessful otherwise. Okay. All right, database also controls concurrency. You've got an airline reservation system. You've got multiple people who are booking seats on a flight. You don't want the same seat to be booked by the same people or by multiple people, so that you have two people assigned to the same seat. So databases manage that concurrency. Okay. We're going to learn about security of databases. For those of you taking my security classes, we talk about different means of access control. And a database system, generally, SQL in particular, SQL in particular, implements what's called role-based access. And what role-based access means is that each user of the database has a certain role with respect to that database. And they're allowed to do certain things to certain views of the data. Okay, so if, for example, you are a travel agent, you can update seat assignments. But if you're a passenger, you can only read your own seat assignment. Okay? So, there's a role of travel agent, there's a role of passenger, and each one of those has a different set of things that they can do. And the controls in a database are very fine-grained. For those of you who take an operating systems class, you have file permissions. Files are, you're familiar with Linux, you have user group other permissions on files. A file is a fairly big thing. Now imagine the ability to control individual fields in that file. That's essentially what the database is providing you with, but they're structuring the data in that file and they're controlling access at that fine level of granularity. And we'll talk about what that level of granularity is. Okay, so we model the data in a database before we implement the database. And the reason that we do that, once again, is it's easier to get agreement on and change a model before you implement the database than it is once you've implemented the database. Okay, so what a data model shows is the data model shows what the data is and how the data is related how each element of data is related to one another. It also defines what the data means, the semantics of the data. And it defines constraints of the data. If I change a particular piece of data here, how does that change affect other data in the database? So we're going to learn how to do data modeling. We're going to learn how to model the data in a database. We're going to learn a relational model for data in a database because that is the primary model that is used in, I forget which percentage, but a very large percentage of the database is used in industry. Later in the semester, we'll talk about other models. We'll talk about object-based data models. But these are still in their relative infancy and haven't been implemented broadly in industry. But we'll talk a little bit about what's going on with object-oriented databases and object-oriented models and hybrid models of object and relational. There are various protocols for exchanging data between a database. Some of you may be familiar with extended markup language, XML. This is a means by which data can be transferred, imported, and exported from a database. Okay. for those of you who are not familiar with XML, if you're familiar with HTML, you know, every element of a web page has a starting tag and an ending tag and something in the middle, like it will say heading, and then it'll have the heading of the web page and slash heading. You know, that's kind of what XML looks like. It tells you what all the elements are of the data, and it labels them with what's called, that defines the meaning of that data. So we'll also learn a little bit about that. All right, let me stop there. Does anybody have any questions about anything that we've talked about so far? Some of this will become a little bit more tangible when we go through some more concrete examples, but this is just definitional for you for the time being. Any questions, comments? All right, if not, let's move on to an example. So, you know, we're here in Ocean County College, and we want to build a database of essentially this course and other courses like it. So, you know, what are the kinds of things that we need to capture about a particular class offered by the college? Any ideas? Any thoughts? Yeah. Yeah, we want to know information about the class itself. You know, obviously the name of the class, course number, good stuff. You know, there are a bunch of things that we want to know about the class itself. What else do we want to know? We want to know stuff about the students taking the class. And there's some things about those students, right? You know, we'll come up with some more here. But we've got classes, we've got students. What else do we have? Yeah, exactly. Who's teaching the class? Anything else? Can anybody think of anything else? Yeah. Grading scale, great. Yeah, they're grades. You guys are going to get grades for different things. What are those things you're going to get grades for? Assignments. Or an overall grade for the class. So, you know, we have these things. We can model this. You know, I don't have all of these things captured in this model. You know, this is a simple model. But, you know, we've got, you know, what college offers. We've got the college, we've got the course, we've got the student, we've got the grade scale. You know, we could add to this model, obviously. You know, this is a small scale model. But this tells us, you know, these are the things we would want to know about a course like this. You know, these are some major categories of things that we would not want to know about this class. And as we said, each one of these has things that define it. Okay, you know, course has course number, it has name, procedures, policies, learning objectives, a schedule, textbook. The grade scale has the letter grade and the point range that corresponds to it, and the grade point value that accounts for in your grades. You guys are students, you have an ID, a name, a phone number, an email, all that good stuff. And you know, instructor has name, phone number, email, office hours. Okay, so you know, you have these major categories of data in this university database example. And then you have things that define it. And the interesting thing about these things is they have relationships. You know, they relate to one another. An instructor is employed by a college. An instructor teaches a set of students. The student is taught by the instructor. So a student earns grade for a course. that's taken from a grade scale. Student takes the course. The student attends the college. The course is offered by the college. You know, we would draw some of the relationships between these things. We have to know how these things relate to one another. So this is the beginning of a data model, and we're going to learn more about this as we go along. But, you know, this would be a model for our data. We would want to draw this picture, and we would want to make sure that we have this picture complete before we go and implement our database. Okay? So if I draw this picture and I walk you through this picture, you can kind of understand what kinds of data I'm interested in for this database. And you can say, hey, Professor Weiss, you forgot about this. Or what, you know, we really need to know, you know, not just the grade for the course, we need an assignments thing. We need to add an assignments thing. Let me make sure I'm writing on a board with those. We need to add an assignments thing here. You know, a student does an assignment, and the student receives a grade for the assignment, you know, that kind of thing. So we could add things, and we could extend this database. And when we go through that process with our users, our customers of this database, we can get to a design that makes sense for the database, and then we say, okay, we're ready. So that's the purpose of doing a data model. You know, I want to give you guys an idea of a data model. And you'll see some weird notation on the diagram. You see these things that look kind of like chicken feet at the end of the relations, or you see these little lines. What do they mean? Well, what they mean is they mean the ordinality of the relationship. So, for example, the chicken feet means many, and the line means one. So a teacher teaches many students. A student is taught by many teachers, you know, more than one teacher. You know, that's the way to read this. This slide says that there are many instructors for each student. Okay. On the other hand, an instructor is employed by only one college. You know, they're obviously, you know, there are adjuncts who teach for multiple colleges, but for the purposes of this model, you know, we're saying an instructor is taught or is employed by only one college. Okay, so that's what those lines mean. And when we get into entity relationship diagrams, we're going to learn more about this notation and other notations for representing the data model. Okay. This is a model of a university database that we can review, we can complete, and we can use this as the basis of our database. But how does this relate to what we're going to implement in our database? Who knows what these boxes might be when we implement this? These boxes are a table or a relation in the database. Okay? The words next to the boxes, you know, the things that comprise these data elements are the attributes or the fields of those tables. Okay. They were originally red. I guess the color changed when I put them on the new slide. They were supposed to be red. These would be red. All right. You know, your GPA might be a calculated thing. You know, we might put together a query that uses the relationships to figure out what your GPA is. Okay, so that would be a query that we would write. And there are several analyses and views of this data that's possible. You know, if I'm an instructor, you know, or if I'm the administrator of the college, I may not care so much about the individual grades of the students. I only want to see, you know, what courses are being offered and what schedules for the courses are being offered. So I can dice and slice this database in a variety of ways depending on who my audience is. So we're going to learn a little bit more about the terminology here, but, you know, hopefully you guys are starting to see how these databases are structured and getting a feel for how they're implemented. So let's look at a relation in a database. Oh, let me erase my When I was a kid, by the way, there was a TV digression here. When I was a kid, there was a TV show for kids. And for that TV show, you had to buy this plastic thing that you put over your TV. And at various parts of the TV show, they'd say, oh, help the hero of the TV show by drawing something to help him on the screen. And the kids would draw something on this plastic thing to help him. And, you know, when I was little, I didn't know I needed a plastic screen. So I used a permanent marker on a TV screen. And my parents weren't too crazy about that. But anyway, so I might repeat that mistake. That's why I wanted to make sure that I was on a whiteboard before I started drawing on the screen. All right, that has nothing to do with databases, and that's probably gratuitous and wasting your time, but there it is. Anyway, so here is an example of a relation. You know, here's an instructor table. The instructor has an ID, the instructor has a name, the instructor has a department, and the instructor has a salary. Okay, this thing is called a relation. It's going to be implemented as a table in our database. Sake of this discussion. All right, the rows in this table are called records or tuples. Okay, each instructor in this database has a record associated with him or her. So each row is a tuple or a record. Each column is a field or an attribute in this table. Okay, so these are some words that you're going to hear. You're going to hear relation or table. That's this whole thing. A row is a record or a tuple, and a column is an attribute. Okay, so our attributes of this particular table are ID, name, department name, and salary. Okay, and this whole business of a relational model, by the way, was invented by this guy, Ted Codd. And you're going to hear his name later on when we talk about normalization. But by the way, these slides are taken directly from the publisher of our book. I talked to them, but they developed. You know, you'll see the reference in the upper corner there. But Ted Codd is the guy who invented the relational model, 1981, and won an award for it. And unlike some of the guys who invent this stuff, was probably not a bad guy, because some of the people who invent stuff like this have their own little personality problems. All right, but let's look at two tables here. You know, here we have an instructor table, and here we have a department table. So we take these two tables, and you know, we see that the attributes of the department table include a department name and a building and a budget for the department. Okay. Why are these two tables instead of one table? Why don't we just put this in one table? Yeah. Easier to read? Yeah, that's certainly one reason. That's certainly one reason. So notice we have multiple entries for computer science here. For those entries for computer science, we would be repeating Taylor building and a $100,000 budget on each of those rows. So we would have multiple copies of that same data for every record of this database. Now, these are fairly small tables, so that's not a big deal from a storage perspective, you know. But you can imagine that as these databases get bigger, having that kind of information repeated so many times may not be the best from a storage perspective. Also, you know, if I have a record here that says Srivanathan Computer Science 65,000 in the Taylor building, and computer science has a budget of 100,000. If I change the budget for the computer science department, you know, we win a great grant for another $10,000. I don't have to update it in all the places that that $100,000 appears, right? I only want to update it in the one place. So that's why we break these things into multiple tables. Everybody good with that? All right, but you know, we have to be able to answer questions. What kind of questions do we want to answer about this? You know, I've just promoted myself. I'm now the head of the computer science department. All right, so I'm now head of the computer science department. And I'm thinking I need another instructor in the computer science department. Well, I look at these salaries, you know, Srinivasan is making 65,000 and Brank is making 92,000. And I have an overall budget of only 100,000. Wow, that's a bad example. Only 100,000. I'm already over budget, but you know, I want to know how my salaries compare to my budget, right? So I might want to write a question or a query that tells me how much of my budget I've spent. So I need to be able to put these things back together. The way I put these things back together is I look at the department name here, and I find out what the department name is here, and you can see that these two tables are related, right? They're related by department name. Everybody good with that? So I can match up the department names, and I can put these tables back together and do a little bit of a calculation to figure out how much of my budget I'm already spending on salaries that I've already got for these instructors. So that's how the relational model works. You know, you have to be able to store things efficiently and in such a way that you don't have to update them a bunch of different places. But at the same time, you want to be able to put these things together in unique ways, you know, to answer specific questions about the data. Do you guys have any questions? Remember, phrase your questions in the form of SQL. No, I'm just kidding. You guys have any questions about this? All right. So this is a real simple example. But, you know, those lines that we drew on the other page, those relationships that we drew on that data model are implemented by having common fields in one versus another relation. And when we put those things together to answer questions, it's called joining the data. Okay? So we're going to learn a little bit in our next lesson about what's called relational algebra. You know, the various operations that you do on a relational database. So we'll get into that in our next lesson. But a join is a very important operation because that's the thing that lets you put this stuff back together to figure out useful things about it. Okay. Talked a little bit about the layers of a database system. You know, you have the physical implementation. And the good thing, as I said, is that most database management systems hide a lot of the details of the physical implementation from you or abstract it so that you don't need to worry about it. But you do need to worry about the physical design of your data. And I'll explain that. So there's a physical view of your data. There's a logical view of your data, logical definition of your data. And then there are various views of your data. The views of your data are dependent on the audience that needs to use the data. As I said, you know, as the head of the computer science department, I may require a different view than an individual instructor would require. You know, when we go into Canvas, you know, I've got my instructor view that shows me everything. And then I can click on student view here. And I see that you guys can only see this much of that view. All right, so different views are provided of the same database to different classes and categories of users of that database. So you have the view level of the database as well. So a database management system needs to allow us to manage the physical level, the logical level, and various views of the data. my slideshow mode here. By the way, I just noticed my mouse is upside down. All right. So, talking about these views in particular, the logical schema defines the logical structure of the database. So, to define the logical schema, you're essentially converting from the data model that you built into a specification of what each of the relations in the data, or each of the tables, and what their attributes are. That's the logical schema. The physical schema specifies the implementation of that logical schema in the database. So things like what are the data types associated with the various attributes? A student name will consist of a last name of 24 characters, let's say, and a first name of 38 characters, whatever the definition is of that are going to implement that logical schema. So you define the logical schema, and then you get into the details of how that's going to be implemented in terms of the data types in the database, and you specify that. And you can also specify in the physical schema any dependencies between relations in the database. So, those things that I showed you, the way the field, the department field, which was the way that we put those two tables together, you would specify that relation as you define the physical schema by specifying what's called keys in the database. And I'll explain that in a little bit. An instance of the database, tells exactly what are the values of each of the records in the database at a given point in time. So each record has these values in these fields. That's an instance of the database. Okay, so we want to make these things relatively independent. We want the physical implementation or the logical implementation to be abstracted from the physical implementation. So, we want to be able to develop applications to the logical schema. We don't want those applications to have to be concerned with how the database is actually physically implemented. Okay, so that's why we separate these. We want to be able to, for example, if we decide that there's a new database management system out there that does things better than the one we're using, we want to be able to move to that without having to change our whole application. So, that's why we separate the physical design from the logical design. Okay, data definition language. This is the means by which we specify the schema of the database, the physical schema of the database. So you can see here, for those of you who program, you'll see here, this looks very similar to your data declarations in a program. But what we're specifying here is we're specifying what the various fields that implement this relation are going to be in our database. The ID is going to be 5 characters long. The name is going to be 20 or less characters. Varchar means it can be 20 or it can be less. Okay, likewise, the department name, the salary is numeric. It has 8 places and 2 decimal places. Okay, so that's how we specify the definition of the implementation of this particular relation. Right? So that language that we use to specify the definition of the data and the structure of the data is called the data definition language. You know, that specifies how the database will be stored. That specifies the schema. It tells which are the keys. A key is, you know, a field that uniquely identifies a specific record in this table. So in this case, ID would be a good key because we can assign unique IDs to each instructor. And that would be the key field of this table. So if you want to know a particular instructor from another table, you want to reference a particular instructor from another, you can reference that instructor by their ID, and that would point to the thing that contains the information about what their name is and what their department name is and what their salary is. Okay, so a key field is the means of accessing the data. Okay. And the other thing that the data dictionary contains that you can specify in the DDL is the access control rules. You know, who can access what data. So all of that is in the data definition language. Then there's another piece. So DDL is one piece of what we're going to learn in SQL. The other piece is the data manipulation language. Data manipulation language is the means by which the data is going to be retrieved from the database. Okay, so these are essentially this is essentially the logic that tells what you want to extract from the database. And you guys who do programming are used to procedural languages. So while this, do this, step 1, step 2, step 3. What we use in database management systems is more of a declarative language. We don't tell how we want the system to retrieve the data. We just tell it essentially what data we want to have retrieved. And the database management system then does the work to figure out how to extract that data. Okay. So you guys have a homework assignment that's just essentially get Microsoft SQL Server working for you, you know, get access to Microsoft SQL Server and run a very simple program. And the program is a one-line program. And it says select star from student data where name equals of your last name. Done it right. I think 200 is done it right. But that's a declarative statement. You know, you're saying select all of the fields from a table called student data. Where last like W% is my last name. So, you know, this just tells the database what I want. I want all those records, all those student records where the last name begins with a W. I don't tell it, you know, first pull, you know, read the first record, read the second record, read the third record, loop through that until you find all the W's. You know, that would be a more procedural implementation. So, you know, that's a declarative. You know, when we talk about declarative versus procedural, that gives you an idea. You know, for those of you who might write this program, you might read one line at a time from the file until you find, you know, parse it and find the last name that begins with W and pull all those records. Okay. This is easier. Okay, SQL. So I already gave the select example, but SQL stands for Structured Query Language. It is a declarative language for retrieving data from a relational database. And the good thing about SQL is it's a standard. And it's a language, if you learn to write in SQL, you can run SQL programs against Microsoft SQL Server or an Oracle database or any relational database, because this is a standard. I say quote standard because every time something is implemented by somebody who's trying to sell a product, they change it in such a way that it advantages the sale of their product versus alternative products. So you will see some differences in the implementations of SQL, but it's supposed to be driven by the American National Standards Institute, ANSI, and it's supposed to be standard. And that's what we're going to learn. And that's why I picked Microsoft SQL Server rather than MS Access, because at least Microsoft SQL Server is closer to ANSI SQL than MS Access is. MS Access is a disaster. The other one you might see is MySQL provided by Oracle. Originally, I thought we might not have free access to Microsoft SQL Server for a bit. So I rewrote this entire course for MySQL, and then I found out that we can still use Microsoft SQL Server. But those two are very close. And that shows you how close they are, that I was able to rewrite all the queries that I wrote. I was able to easily convert all the queries that I wrote for Microsoft MySQL. But, it's fairly standard. And the other thing that's fairly standard is there are interfaces for integrating queries, these declarative statements, into procedural languages. And we're going to learn those interfaces also. One of them is called the Java Database, JDBC, and the other one is provided by Microsoft, or was driven by Microsoft, and that's called ODBC. And both of those are libraries that you can get with your Java environment or with your Visual Basic environment or with your other programming language environments that will allow you to integrate these queries into your programs. And you would use those, for example, if you were writing a web client, a Java program in a web page that would query your database. Okay, so we'll learn those as well. All right, I've been doing a lot of talking. Any questions on any of this? Okay. So, Turing machine. Yeah, I forgot to. Anybody know what a Turing machine is? Anybody know who Alan Turing was? All right, anybody see The Imitation Game? Alan Turing, if you ever hear about Alan Turing, Alan Turing is by many, myself included, considered the father of computer science. And Alan Turing originally became famous for breaking the Enigma machine. This was a Russian encryption device, not a Russian, I'm sorry, German encryption device during World War II. Alan Turing invented a machine that would help to break the codes of the Enigma machine. And it was very mechanical rather than electronic, which is amazing. It's just amazing that they could implement this thing. But the theory that Alan Turing used to invent that machine is that when something starts in a state and then something happens, there's an operation that takes place that moves it to a new state. And if you string these things together, you can implement some complex logic. And that's called a Turing machine. That's the principle of a Turing machine. A machine that changes from one state to another state based on a set of operations. And what does that sound like? That sounds to me like a computer program, right? That's what a computer program does. So Alan Turing essentially invented procedural programming. So that's why you hear this business about a Turing machine. This is a state machine that goes from state to state. a declarative language is not a Turing machine. It's in, underlying the implementation of that declarative language might be is a Turing machine, but a declarative language itself is not a Turing machine. But that phrase here, and you're wondering what it means. That's what it means. That a Turing machine is this thing that transitions from state to state, and it was invented by Alan Turing, who is, in my opinion, the father of computer science, one of the fathers of at least programming in computer science. Okay. So yeah, so we've already talked about, how SQL is not procedural, so therefore it's not a Turing machine. That's all that needs to be said about that, other than the interesting history lesson that goes through. Okay. So this is how our publisher identifies the database design process. You have to decide on what the database layout is going to look like. How are you going to lay out the relations and fields and attributes of your database? That's the logical design. What data do you need? How is it going to support your business processes? Okay, so you need to make the business decision of what data you need to support your business processes, and you need to make the computer science decision of how you're going to organize that and how you're going to structure it and break it up. That's the logical design. And then the physical design is deciding how you're going to physically implement that in your database. And if you remember in our last class, and I'll bring it up again, because it'll mean we'll be looking at this diagram a lot, I think, over the course of this class. So let me bring up this diagram again, because this is my diagram. Oops. Oh, gosh, I'm losing it here. See, I don't wear my glasses because they fog up when I'm wearing this this mask. Here we go. But this is the way I look at the database design process. These things here are the logical design. Boxes here, these 4 boxes, and we're going to do those as part of our final project. And these things here are more the physical design and implementation. All right? The logical, physical. This is the process that we're going to go through for this class. Okay, back to our slideshow here. Something? No, that's it. Okay. All right, so the database engine itself hides a lot of the implementation from us, as I said. And these are the things that are in the database engine. It manages the storage. It processes the queries, that declarative stuff that we write. The database engine is essentially like a interpreter for the queries that you put into it. And when it processes those queries, it understands the physical implementation, and it will optimize your queries for you to make sure that it's pulling the data out of the database in the most efficient way. Okay? So the query processor component it says, okay, what does this person want? This is the data that they're asking for. The query processor says, okay, what's the most efficient way to get that data for them? And the query processor will then pull the data that you want. The other piece is the transaction management component. If things have to be done together, this is the thing that makes sure that either the entire transaction is successful, or it does what's called a transaction rollback. It pulls back that transaction so that none of the operations take place. So, once again, if you're doing an electronic funds transfer and the withdrawal happens, but the deposit doesn't happen, the transaction manager will manage that for you. So those are the pieces of the database engine. Okay, the storage manager, these are the things that it does. It interacts with your underlying file system. Ultimately, databases are implemented as files on your computer, on your server primarily. So it will interact with the OS file manager, and it will make sure that data is stored and retrieved in an efficient manner. And it will maintain indices of the data. These are things that tell it more quickly how to find the data that you're looking for. So, there might be hashes, there might be, each database relation might be implemented. For example, this is just an example. Don't think this is the only way that it can be done. But, in your operating system, you might have a file that has the individual records, record 1, record 2, record 3, record 4, record 5. Along with that file, you might have what's called an index file that says record 1 is at sector X partition Y. And that might point you, or let's say record 5 is, that might allow you to get to this place much more quickly than if you just scan a file sequentially. So, the database management system, the storage manager, implements this faster way of accessing the data. Okay, and that's hidden from you by the database management system. You don't know that stuff when you're writing your queries. That's just something that the storage manager. It also makes sure that your data is maintained that the integrity of the data is maintained. It might do automatic versioning of your data, so that if something bad happens to your database, you can get back to a previous version before that bad thing happened. Okay? So it does all of those things to manage the storage of your data in your database. Okay, so it implements the data files that contain the data itself. It implements the data dictionary. What are the various fields in that table? What are the various tables? What is the meaning of the various fields? And it implements the index, which is the thing I just showed here, that might provide you the faster access to the data in the database. Okay, the query processor. As I mentioned, there are two languages. The data definition language, that defines the structure of the data. The query processor has to read that data definition language and translate that and communicate with the storage manager to set up the tables and relations in the database. The DML, those are these select statements and things like that to retrieve data. The query processor has to interpret those. It has to optimize those. And it has to execute them against the database. So, all of those things are done by the query processor. Good. So, here is a flow chart for query processing. The query comes in, the query processor parses it and translates it, and then it goes through an optimizer to make sure that it's, that the data retrieval is going to be done optimally with respect to the implementation. Then it decides how it's going to execute that. It evaluates the query, and it generates the output. So this is how the query processing portion of the database system works. Transaction manager. If two people are trying to access the same piece of data at the same time, the transaction manager does the concurrency control. The transaction manager will also make sure that atomicity is maintained for things that have to happen together. Okay, so that's what the transaction manager does. And you know, if something happens during the execution of a transaction, the transaction something bad happens, like a power failure or a crash or something like that, the transaction management system ensures that the database may be returned to a sane state upon restoration of service. But what you're going against is you're going against the server that stores the database. You know, databases are generally multi-user types of things. They run on servers, so they can be workstations. So the processing and storage on the database can be distributed across multiple servers. But for databases that have high performance demands, might require multiple servers to be processing queries. Likewise, for databases that are very large, you may need storage on those databases partitioned across multiple servers because of the size of that database. So you'll see all of these things, you know, you'll see all of these various architectures, talk more about them. And the good news is the language that accesses them is all the same. Still going to use SQL. You don't know what, you know, you guys are going to work with SQL on a database that runs on your computer there. But that SQL code could also run against a much larger database. But what you're learning is very practical, and you know, all the details of how that's of the database underneath are hidden from you by this nice abstraction that we call this SQL language. Okay, this is an example of a database implementation. You know, you have the storage that contains the data, the indices, the data dictionary. By the way, if you're having trouble seeing this, you can join the WebEx and you'll see it. But you know, the data that's stored is the data itself, the data dictionary that defines what the data means, the indices that help access that data, and statistical data from the database management system itself that talks about, you know, the usage of the data. See the query processing up here. You can see the storage manager, you know, how the query processing interacts with the storage manager. And you can see the various pieces of the query processor. So this is kind of a cheat sheet on what a database management system looks like. And, you know, this case is a centralized thing. You might have these functions distributed in various ways across multiple systems. Okay, so there are various tiered architectures for database systems. I mentioned that they're client server. You know, a two-tiered architecture is where you have a client going to a single server. And that server does the processing, the transactions, and the storage. Okay, that's a two-tier architecture. But you can also have a three-tier architecture where the client machine is a front end and it interacts with an application server that does the actual querying and goes against the database system that actually stores the data and accesses it. So that would be a 3-tier architecture. Okay. So 2 and 3-tier architectures are common in database management systems. The client can do the input and output and also generate the query to go against the server. Or the client could just be responsible for the input and output, send that to an application server that builds the query, and that would go against the database server that retrieves the data. And here's a picture of that. All right, so there are different types of users and different types of roles with the database. Depending on the job that you have, you may be performing in one or more of these roles. The person that's concerned, or the group that's concerned with the allocated servers, whether you have one server or multiple servers, and how you break up the data across those servers. The physical implementation is the role of the database administrators. Database administrators decide how to optimize the data from a physical implementation perspective, what servers to use, how to distribute things across the various servers, and how to administer that information. They also administer user accounts, who's allowed to access the data. So, there's a strong relationship. If you've done any system administration, you may also wind up doing database administration. That could be part of your job as a system administrator, or it might be an additional job. So then we have our analysts. So these are the people who are expert on what data needs to be retrieved to answer what questions. These are people who understand the business processes of the company, and they know how to build the necessary queries to extract that information from the database. You have your application programmers. They're the people who might build the interfaces to those queries that the analysts provide. They may implement those in terms of screens on a client, and may implement them in terms of how they interact with the query processing. So then these application programmers deal in procedural languages. Analysts deal in SQL. Okay? The primary language of an analyst is SQL. The primary language of an application programmer is a programming language like Java. The primary language of a database administrator is Oracle administration or SQL Server administration, or whatever database tool they happen to be using to implement this. Okay. Naive users, their primary language is a web browser. A screen on a web browser, or a specially implemented screen separate from a web browser. They just type. They're just essentially typists. They type in information. They might be travel agents. They may be nurses. They may be financial analysts. They are not sophisticated computer users. So all of these different types of people interact with the database system. Okay, this defines each of those roles in more detail. Here you can see that a database administrator is very similar to a system administrator in terms of their roles relative to the database versus relative to a computer system. But you can see, these are the kinds of things that they do. Okay, and I'm not going to go through the history of database systems. The only thing I'm going to tell you You can read this here, or you can read it. The important thing is that Ted Codd defined this relational model in the late 60s, early 70s, won an award for it in 81. What databases were before that? They were very file-based and very binary. I guess is the base. Binary data in files, and retrieving them was very hard. So relational databases really made this a lot easier, and that's why relational databases are so widely used today. And where we're headed is we're headed more toward object-oriented database systems. You guys use object-oriented programming languages. A lot of database systems are not only storing data. Yeah, who can tell me the difference between an object-oriented language and a non-object-oriented language? What makes a language object-oriented? What's an object? It has two things. Yeah. Data is one of the things that comes with an object. An object has certain pieces of data that, data that it has as part of it. But there's something else that comes in an object. When you guys write objects, you're writing certain things for that object. There are methods to an object. An object has methods. And database systems store data. Relational database systems store data. Object-oriented databases not only store data, but they store the methods that work on that data. That's a new type of thing that is being implemented that hasn't been practically adopted across the industry, but it's a direction that the industry is headed. So not only will these databases store the data, but they'll store the ways that you'll interact with the data. Special ways for special types of data. So that's what's coming. That's the future of database management systems. All right. Yeah, bigger and bigger databases in the 2000s, and Oracle's doing things with NoSQL. I guess more intuitive means of extracting data from databases. Those are other things that are on the horizon. And I'm finishing pretty much just in time. So, just to wrap things up here, in terms of those of you who have Windows, want to do your homework at home rather than using please make sure to download Microsoft SQL Server onto your computers. I'm not great. All I'm asking you to do for this assignment is download Microsoft SQL Server and load the backup that I've provided. Let me show you how to do that really quickly, because there was a question on that. So let me do that really quickly and run that very simple query. So let me show you how to load a backup on Microsoft SQL Server Management Studio. Bring that up. Once you've downloaded and installed SQL Server and SQL Management Studio, you'll bring up SQL Server Management Studio. You'll log on using whatever authentication, using the default authentication. Mine is not the default authentication because Ocean County College owns my computer and they made me do something else. So you log on and you'll right-click on database and you'll click on restore database and you'll click on device and add, and then you'll find the backup file, which is right here, grades.back, and you'll hit OK and OK and OK. and you hit OK, and it will load that database. And after you've done that, which I've already done, you can click on this plus sign of database, and you will see this grades database there after you restore the backup. Okay. So that's, if any of you have any questions on that, please remember I'm recording this session, so the recording will be available. So you will see exactly what I did if you go to the end of the recording, and that will show you how to load that backup. But that's what you're expected to do by, I think it's the 14th, is it? The 14th. That's what you're expected to do by the 14th, is to have this loaded and have that backup loaded. If you don't have a Windows PC, and one of you has already given me your name, we'll get you on the virtual machine. In the meantime, you're going to have to do this on a school computer. So I apologize for that. You know, we'll try to get you up and running on the virtual machine as soon as possible. But if you don't have a Windows computer at home, you'll have to find a school computer to do that on. And let's see if Andrea answered my question about where you can get a school computer. The lab's in the library, room 216. All right, so that's it for today. Everybody have a great rest of your day, a great weekend. I know this was a lot of talking today. I promise future classes will be more hands-on. So hopefully I didn't bore you too much. And you guys have a great weekend, and we'll see you on Tuesday.